The last section in chapter 12 would be a review of conic sections. You may have seen conic sections in your trig class. Of course, that was probably quite some time ago. So we will be reviewing conic sections. If you haven't seen conic sections, no worries, it's pretty easy to catch up on them. So here's the basic idea. You have a cone, and in fact you have two cones that are attached by a common vertex. Now, if you take a cone and you intersect it with a plane, you're going to get these curves, which is what we call our conic sections. If you intersect the cone with a horizontal plane, what you end up with is a circle. If you move that plane and you slant it a little bit, the intersection would be an ellipse or an oval. Slanting that plane even more so that it's almost vertical, you'll get our familiar parabola. And then if you have a vertical plane, you get what's called a hyperbola. It looks like two parabolas, or a hyperparabola. Now the special cases are if you intersect at the vertex of the two cones. If you intersect with a horizontal plane, then you just get a point of intersection. If you slant that plane and it passes through the vertex, then you get a single line. And if the plane passes through the vertex and it's completely vertical, you get a pair of intersecting lines. In this section, we're going to be concerned with three of these conic sections, and that would be an ellipse, a parabola, and a hyperbola. So the first thing we're going to do is we're going to look at the parabola, which would be the conic section that's familiar to most of us. Now, in previous algebra classes, we would have written the general equation for a parabola as y equal to ax squared plus bx plus c. In this section, we're only concerned with parabolas that have a vertex at the origin 0, 0. So in that case, this bx plus c is going to be gone. Also in this section, we're going to look at the equations in a different way. Instead of writing it as y equal to something with an x squared, we're actually going to solve for the x squared. The reason we're going to do that is because the y over a, which we're going to write in a different way, is going to give us a lot of information about this parabola that has a vertex at 0, 0. If you look at the diagram, we have a parabola. The vertex is at the point 0, 0. And now there's some really nice properties with a parabola. So a parabola has a property that there is a focus. The focus is a point that's not on the parabola. We call it a focus is because it's where all the energy is focused. And when you think of things that are parabola shaped, like an amphitheater, the shell in Waikiki is parabola shaped. The lens of your eye, the headlight of a car, a satellite dish. These are all things where it's easy for us to admit sound or light, energy of any form. So this is a really nice conduit for different types of energy. On the opposite side of the focus, and this focus, the distance from the parabola, if you go in the other direction, you're going to have what we call a directrix. The directrix is a line. Okay, so it's the same distance away from the vertex as the focus is. So the property is that if you pick any point on your parabola, the distance from the focus to the point is going to be the same as the distance from the point to the directrix. And that would be true of any point that we pick on this parabola. Okay? The distance to the focus is going to be the same as the distance to the directrix. Well, let's look at this box that describes what a parabola is. Okay, so we have some real number p. Let's say the focus is at the point 0, p. So p is not equal to 0. So this focus is going to be, it's going to have a y value. So the focus is actually going to be on the y-axis. Well, the directrix is going to be y equal to negative p. So the directrix is going to be a horizontal line. It's going to be symmetric about the y-axis. The equation is going to look like this. X squared equal to 4py. And now if p is positive, then it opens upward. If p is negative, it opens downward. Well, let's say the focus is at the point p comma 0. So that would mean this p would be on the x-axis. So if the focus is on the x-axis, we're looking at a directrix that is a vertical line. Its equation would be x equal to negative p. So the symmetry is about the x-axis. The equation in this case is a y squared equal to 4px. If p is positive, then it opens to the right. If p is negative, then the parabola opens to the left. Here are the 4 possibilities. Again, if it's an x squared, then that would indicate a parabola opening up or down. But if p is greater than 0, that means it opens up. So if you have an x squared, it's going to open up or down. P less than 0 or negative means it opens down. So y squared would be left or right. If p is positive or greater than 0, it opens to the right. Less than 0, it opens to the left. Let's go ahead and do some examples. Let's say that we needed to find the focus and the directrix of the parabola, and then we also wanted to sketch its graph. Well, if you look at this equation, it's an x squared. So this is similar to the generic equation, x squared equal to 4py. So if we compare the two, that must mean that 4p is equal to negative 12, which means that our p value is equal to negative 3. Since this is an x squared, it means it's a parabola that opens up or down. And since p is negative, that means our parabola opens down. So let me start drawing my graph. So remember, our parabola has a vertex at the origin, 0, 0. And I see that p is equal to negative 3. Remember that p represents our focus. So the focus is actually not on the parabola. It's going to be 1, 2, 3. It's going to be here. And then our parabola is going to open down. And I'm hand drawing this, so it's probably not going to look so good. So if the focus is at the point 0, negative 3, then that would mean if we go up 1, 2, 3, then we go ahead and we have our directrix, which is a horizontal line. So the equation is y equal to positive 3. So we found our focus, which is the point 0, negative 3. And we found our directrix, which is the equation of this line. And we sketched the graph. However, we really don't know how wide this is, so I do need to get a couple of points. So you can just plot some points. I use this really interesting property that we have with parabolas that says if you look at the line that passes through the focus, right, then you'll get these really nice points. So although this is not part of the graph, if you look at this imaginary line, the distance of that whole piece is going to be the absolute value of 4p. So in our case, p was -3. So it's the absolute value of -12, which is +12. That would be the complete distance. So if I just look at half the distance, this distance here should be 6. So the distance here is along the x-axis. If I just simply take 6 and add it to my x-coordinate on my focus, then I get this point here, which is 6, -3. And this is a distance 6 as well. So if I take that 6 and I subtract it, because I'm going in the negative direction on the x-axis, subtract it from the point 0, -3, I get -6, -3. So we do need 3 points on our parabola. We have our vertex, and we have these 2 points so that we can see how wide our parabola is. Now the other important information again would be the focus, which is a point that's not actually on your parabola, and then your directrix, which is the line opposite of the focus. Well, what if we don't have an equation? What if we just have some information and we need to find an equation? Okay. So let's look at this information that we have. We want to find the equation of a parabola with a vertex at the origin. It's symmetric about the y-axis, and it's passing through the point 2, -6. Well, it's symmetric about the y-axis. That means that it's going to take the form of x squared equal to 4py. This would be a parabola that opens up or down. So we just have to figure out what the p-value is. Well, we have an equation, and we know that it's passing through the point 2, -6, so we just have to put in 2 for x and -6 in for y. And we'll have 4 is equal to 4p, y is -6. In other words, -1/6 is equal to our p-value. Our equation would be x squared equal to 4 times -1/6 times y, or in other words, x squared is equal to -2/3 y. And we're done. We found the equation. Okay, so your equation is either going to be an x squared equal to 4py or y squared equal to 4px. It depends on the information that you're given. So let's move on to some of our other conic sections. So we're going to look at an ellipse, which is a stretched out circle. When we talk about an ellipse, it has the property that it actually has 2 focuses, which we call foci. Okay? So there's a center, and there's 2 foci. Those are the 3 major points. None of these are on our ellipse, okay? But they do have this really nice property that if you take the distance from any point on your ellipse and you look at the distance from one foci and the other foci, if you add those up, it's going to be equal to 2a. And that would be this equation up here. A is one of your vertex. And here we're just concerned with ellipses that have a center at the origin. similar to the parabolas that we talked about that had a vertex at the origin. So again, your A value is just this point here on the x-axis in this first diagram. Now if I look at the other vertex, it would be a negative a comma 0. Well, since there's two vertexes, we call them vertices. So an ellipse has foci, two focuses, and vertices, two vertices. The middle diagram is the diagram of an ellipse where the vertices are on the x-axis. So the vertices in an ellipse is where it's stretched out. Remember, this is an oval shape. So the greatest distance would be where your vertices are. In the third diagram, we have vertices along the y-axis because that's how our ellipse is stretched out. Now if you look at the corresponding equations in these little boxes below, in this middle one where the vertices are on the x-axis, the equation is x squared over a squared plus y squared over b squared plus 1, where a is your vertices. If you look at the third diagram, where the ellipse is stretched out along the y-axis, that means the vertices are on the y-axis, which means your a squared is underneath the y. So wherever the a is where your vertices are. Let's go down to this box that explains all the pieces of an ellipse. So we're looking at the equations of standard ellipse, and these are not shifted, they all have center at the origin. If the foci is plus or minus c comma 0, that means the foci are x values, which means the vertices also have to be x values, which we do a plus or minus a. So that means foci, vertices, if they're both on the x-axis, then it's stretched out horizontally along the x-axis. And the equation would be x squared over a squared plus y squared over b squared is equal to 1. There is this property that if you take a squared, it's going to be equal to b squared plus c squared, and that comes from our Pythagorean theorem. If you take an ellipse centered at the origin, but the foci in this case is 0 plus or minus c, notice that c value is a y value, and the vertices here is 0 comma plus or minus a. The foci are c values or y values, and the vertices are a values or y values. So since both of those values are y values, then this is an ellipse that's stretched out along the y-axis. And the equation would be y squared over a squared plus x squared over b squared equal to 1. And then again, a squared is always going to be equal to b squared plus c squared. So we call the longer axes, and that would be between your two a values, the major axes. And then the minor axes would be between your two b values, and that's 2 times b. In example 3, we're going to find the vertices, foci, and the length of the major and minor axes. And we're also going to graph our ellipse. So first of all, I notice that this is x squared over 36 plus y squared over 25 equals to 1. What I want you to notice is that your a value is always going to be the largest value. So since 36 is larger than 25, that tells me that a squared is 36, which would mean a is 6. And then the 25 would have to be the b value. So that means, or 25 is b squared, sorry. So b is equal to 5. My vertices are going to be x values because the 36 is under the x. So the vertices are simply plus or minus 6 comma 0. They're x values. And my major axes is going to be the distance between my two a values, which is 2 times a. So that's going to be 12. The minor axis, the length between your b values, it's going to be 2 times b, or 10. Now the foci you get because you know that a squared is equal to b squared plus c squared. Remember, the foci are the c value. And you know what a squared is. A squared is 36. You know b squared is 25. So you just have to solve for your c value. So in this case, it turns out to be 11. And then c, if I was solving for c, it would be a plus or minus square root of 11 is equal to c. But technically, we only look at the positive. So our c value is going to be a positive square root of 11. And our foci will be the points plus minus square root 11 comma 0. When we graph this ellipse, it's going to be elongated along the x-axis. It's kind of sad, sorry. And I have my vertices. It's going to be 6 and negative 6. So you can see the distance between those 2 points would be 12. I have my b values as well. It's plus and minus 5, so 0 comma negative 5, 0 comma positive 5. And then my foci are going to be inside, always inside. Let's see, so this would be negative, I wonder if I can squish this in, square root of 11 comma 0. And then I have positive square root 11 comma 0. And that would be the graph of my ellipse. So we found some important information and we graphed. In the next example, we're going to be given some information and we have to come up with the equation of the ellipse. So if we had to find the equation, centers at the origin, notice the vertices in this particular case, the plus or minus 5, that's actually an x value, right? So that would be our a. And it's an x value, so that tells me my vertices are on the x-axis. And then it's passing through the point 4 comma 3/5. Well, since I know my a value is an x value, I know that my equation is going to be x squared over a squared, which would be 25, plus y squared over b squared, and I don't know what b is yet, equal to 1. So I have an equation. I just have to solve it for the b value. But I know that it's going to pass through the point 4 comma 3/5. So if I just put in 4 for x, I'll get 16 over 25. And then 3/5 for y will give me 9 over 25 over b squared. Well, that's equal to 1. So I'm just solving this equation for the b squared. Let me see, if I clean this up a bit, I'll end up with 9 over 25 b squared, and I'm going to take 1 minus 16 over 25 to get 9 over 25 on the other side, which tells me that my b squared, if I continue to solve, is 1. So putting all that together, I have x squared over 25 plus y squared over 1, and I'm not going to write over 1, is equal to 1. That would be the equation of an ellipse with these properties. Our last conic section would be a hyperbola. The hyperbola is probably the most complicated of them all. So if we look at the hyperbola, it's sort of two parabolas, so it's going to have two focuses or foci. And here our center is going to be at the point 0, 0, the origin. So the parabola is going to have a center. The foci are actually sort of like on the inside part of our hyperbolas. So they have a property with distance as well. If you take any point on your hyperbola and you look at the distance from the two foci, if you subtract the smaller from the larger, it's going to be equal to 2a, where a is the vertices. Okay, so it's going to be this distance here. Now we're going to have two types of hyperbolas. Hyperbolas where you have your vertices on the x-axis, and in this case that x-axis would be our major axis. Hyperbola is similar to an ellipse except for there's a minus instead of a plus. So in this particular case it really matters which one comes first because of the subtraction. So your vertices, which is represented by the a value, that always goes underneath the variable where your vertices are on. So in this case the vertices are on the x-axis, so the a squared is under the x squared, and that comes first in the subtraction. In the last example of our parabola, the vertices are along the y-axis. So the equation that we use is y squared over a squared minus x squared over b squared is equal to 1. So looking at this box below, it talks about the properties of a hyperbola. So our foci, if it's plus or minus c comma 0, that means the foci, and if we look at these diagrams, the foci here in the last, and look at the foci in the middle. So if the foci are x values, that means the foci are on the x-axis, and so will the vertices be on the x-axis. And in that case we have the equation where it's x squared over a squared minus y squared over b squared equal to 1. So the property is a little bit different than an ellipse. In this case, b squared is going to be equal to c squared minus a squared. So c squared, if you look at the distance between the two c values, which would be the distance between the foci, that's actually the largest value. So c squared is going to be your biggest value. So when you subtract the a squared, what you have left is the b squared. Or in other words, b squared plus a squared is equal to c squared. Now we're going to look at these asymptotes that come with our hyperbolas, and they're going to help us draw our hyperbolas. So the asymptotes are going to be these lines they'd pass through the origin, since the center of our hyperbolas are on the origin, and they're a guide for us to use when we graph our hyperbolas. The asymptotes are equations of lines. So in the case where the vertices are on the x-axis, the asymptote will be y is equal to plus or minus bx over a. Now let's say that the foci are on the y-axis and the vertices are on the y-axis. Our equation is then y squared over a squared minus x squared over b squared is equal to 1. Again, we still have b squared equal to c squared minus a squared. But in this case, when our asymptotes are on the y-axis, the asymptotes are going to have the equation y equal to plus or minus ax over b. So you switch. If the vertices are on the x-axis, asymptotes plus or minus bx over a. Vertices on the y-axis, asymptotes y is equal to plus or minus ax over b. Went too far. So let's go ahead and graph a hyperbola and specify vertices and foci and find the equation of the asymptotes. So those are the major pieces to it. Well, we have an equation of a hyperbola. We need to find our vertices. So remember, the a value is the vertice, and since it's a y squared first, that tells me that the a squared is 16. So a is equal to 4. That must mean that my b value is equal to 3. So the vertices, remember that's your plus minus a value. They're going to be y coordinates because the 16 is underneath the y squared. So the vertices are going to be 0, comma, plus or minus 4. So I did want to make one comment. In the case of a hyperbola, your a value can be smaller than your b value. It will always be where your vertices are, but it could be smaller. Whereas in an ellipse, your a value is always larger than your b value. So I do have my vertices. I need my foci. I'm going to use the fact that b squared is equal to c squared minus a squared, or in other words, c squared, where your foci are, that would be b squared plus a squared. And we have b squared and a squared, right? So c squared is equal to 9 plus 16. C squared is equal to 25. So c is equal to square root of 25 or 5. And then our foci are, that's going to be 0, comma, plus minus 5. Oops. So now we need the equation of our asymptotes. Remember, if it opens, or if there's vertices on the y-axis, the asymptotes, it's going to be a over b, right? Which would be y equal to plus or minus a over b, so 4/3 x. And this would be our asymptotes. So we found all the important information. We just have to graph. So let me just sketch my graph. To help us with our graph, what we're going to do is we're going to mark off our a and our b values, and we're going to draw ourselves a little box, and that's where our asymptotes will pass through. So our a value is 4, and it's on the y-axis, so we're going to go up and down 4. 1, 2, 3, 4. Down 1, 2, 3, 4. Okay. And my b value is 3, so 1, 2, 3, 1, 2, 3 in both directions. Now I'm going to sketch a box that's going to, or a rectangle that's going to pass through these points. I'm making it dash because it's really not part of my graph. It's just a guide. Now this is a little bit sketchy. And then through the diagonals on this box is where my asymptotes will go. So again, the asymptotes are just guides. And now I can go ahead and draw my hyperbola. I just draw my vertices along the y-axis and follow my asymptotes. So let me just label these parts. The vertices are the most important part. So this would be 0, 4, 0, -4. And then also our guide, which would be our asymptotes. This is y equal positive 4/3 x. And this line here, y equal to negative 4/3 x. And I'm done. In the next example, we're given some information, but this time we're supposed to find the equation of the hyperbola. Okay, centers at the origin. The vertices are, in this case, x values. So I know my vertices will be on the x-axis, which means it's going to be an x squared over a squared. It's going to take this form, minus y squared over b squared equal to 1. So my a value is the square root of 5, which means my a squared is 5. I just have to find my b value, and then I'm done. Well, I have that the asymptotes are y equal to plus or minus, and I'm going to write this as, it's just 2x. But remember, since the vertices are along the x, the asymptotes take the equation y equal to plus or minus b over a times x. So comparing this to, that tells me that b over a is equal to 2. And I already know that a is the square root of 5. So my b value is going to be 2 times the square root of 5, which tells me that b squared is 4 times 5, or 20. And then I'm pretty much done. All I have to do is rewrite my equation, which is x squared over 5 minus y squared over 20 is equal to 1. So although the vertices are along the x-axis, the a value is actually smaller than the b value, which is okay in a hyperbola, but not in an ellipse. In an ellipse, the a value will always be the largest value because that's where your ellipse is elongated. Sorry, I'm a little thick today. Oops. The next concept we're going to talk about is called the eccentricity. Eccentricity, we use E to stand for eccentricity. And now you have to be careful because this is not the exponential e, which is approximately 2.72. Okay, so it's not that e. It's just an abbreviation for eccentricity. And the eccentricity is this ratio that you're going to get between the foci and some point on a directrix. So again, it's a ratio. In the case of a parabola, see we have this point here. If we look at the distance from a point on the parabola to the foci, it's going to be the same distance to the directrix. So in that case, our eccentricity, which is the ratio between these two distance from foci over distance from this line, it's going to be 1. If you look in an ellipse, the distance to the foci will always be shorter than the distance to this line L, which in ellipse they have directrix as well, which is a line opposite from the foci, but we usually don't draw them in the diagram. We usually only do it for parabolas. So eccentricity for an ellipse would be the ratio of the distance from the foci over the distance from this line, which is a directrix. And that's always going to be between 0 and 1, because the distance from the foci is smaller. Now when we look at a hyperbola, if you pick any point on a hyperbola and you look at that ratio distance from the foci and the line, the distance to the foci is always larger. And it doesn't matter if you pick a point on one part of the hyperbola or the other. Distance from foci, distance from the line, distance from foci is always larger. So in a hyperbola, eccentricity is always going to be greater than 1. So if you know the eccentricity for your conic section, then you can identify it as a parabola, an ellipse, or a hyperbola. So here we have a theorem that kind of describes what we just looked at. When you look at the distance from a foci over the distance from a line, that's our eccentricity, equal to 1. Our curve is a parabola. Between 0 and 1, the curve is an ellipse. Greater than 1, the curve is a hyperbola. The following box is just a summary of the major points that we've talked about so far. So there's talks about the major axes, vertices, minor axes, vertices for ellipse. We have foci, directrices, and we have the eccentricity and properties that go with it. So if you look at these values that we have talked about, and here D is going to stand for our, we're not going to use P here, we're using D for directrix. So if you look at all of these variables that we've talked about, like an A for vertice, a B for the shorter distance, a C for the foci, and a D for directrix, and we have these variables A, B, C, D, and E for eccentricity, then we have the following relationships. That foci is equal to vertice times eccentricity. The directrix is equal to vertice over eccentricity. And then for ellipses, we have b squared is equal to a squared minus c squared. For hyperbolas, we have b squared is equal to c squared minus a squared. Okay, so it gets switched around. So we're going to look at finding the equation of an ellipse that's centered at the origin, and we have vertices. But this time we're given information about the eccentricity being 1/3. Well, since my vertice is this plus or minus 9, sorry, that would be my A value, and that's on the y-axis, right? And I know it's an ellipse, so I know my equation is going to be y squared over a squared, since the vertices are on the y-axis, plus x squared over b squared equal to 1. And I know that my a value is 9, so I know that this is going to be y squared over 9 squared, or 81, plus x squared over b squared equal to 1. Okay, and then I'm kind of stuck. I know that b squared is an ellipse is equal to a squared minus c squared, but I don't have, so this is what I do know. I know that the b squared is equal to a squared minus c squared. And I do have a squared, I just don't have c squared, so I can't really find the b value. I also know that the c value is equal to a times the eccentricity. So maybe I can use that, because I do have my a value and I do have my e value. So I'll have c is equal to 9 times eccentricity is 1/3, which gives me a c value of 3. So now that I have a c value, I can go back to this equation, b squared equal to a squared minus c squared, to get b squared is equal to 81 minus 9, which would just be 72. And I don't really have to solve for b, because in the equation, and that's all it's asking me for is an equation, in the equation I just need b squared. So this would be y squared over 81 plus x squared over 72 equal to 1. And I am done with that. The last concept we're going to look at is in this box below. We're going to look at polar equations of conic sections. So it's application of eccentricity. So if you have a conic section, and this time we're not looking at a vertex or a center at the origin, this time we're looking at a focus at the origin. Okay? And let's say you know the eccentricity E. Then we're going to have these following polar equations to describe our graph. Okay, the first polar equation, remember the polar equations are equal to, that's going to be E times the directrix D over 1 plus E times cosine of theta. Again, this is not the exponential E, this is eccentricity times cosine theta. So if you have this form of the equation, then the directrix is going to be x equal to d. Since the direction is an directrix is an x value, that tells me that my vertices are, it's going to be a vertical line, so my vertices are probably on the x-axis. And then if you have E times d over 1 minus E cosine theta, then one directrix would be x equal to negative d. So if your equation is with respect to sine, so same equation, but instead it's going to be a 1 plus the eccentricity times sine, or 1 minus eccentricity times eccentricity times sine of theta. I can't speak, sorry. then your directrices are going to be a y value. It's going to be a horizontal line, and it's either going to be d or negative d. If eccentricity, again, just a reminder, if the eccentricity is between 0 and 1, the conic section is an ellipse. If it's 1, it's a parabola. If it's greater than 1, it's a hyperbola. So let's apply what we looked at in the box. If I look at this polar equation, it's with cosine. It's not quite in the correct form because remember it was supposed to be a 1 plus cosine theta. So let me first write this in the correct form where there's a 1. So that would mean I would factor out the 2 to get 1 plus 1/2 cosine of theta. And then reducing the 2 top and bottom, my equation R is going to be 2 over 1 plus 1/2 cosine of theta. So if we compare it to the general formula, that tells me the 1/2 in front of the cosine, that would be eccentricity, and that's equal to 1/2. So since my eccentricity is equal to 1/2, that tells me that this is going to be an ellipse. So I know the type of equation I have to have. Now I know that the numerator 2 is equal to the eccentricity times the directrix. And I know eccentricity is 1/2. So that tells me that 2 equal to 1/2 times d, which is a directrix, which tells me that 4 is equal to a directrix. So that tells me from that general form that one of my directrices is x equal to 4. In an ellipse, the directrices are outside of the ellipse. Let me go ahead and start sketching a graph to see what's going on here. All right. So again, I'm just hand drawing this. Now I have 1, 2, 3, 4. And I'm going to draw this directrix. Which is, the equation for that would be x equal to 4. That should be one of my directrices. I should have another one. I also recall that our foci is going to be at the origin, or at least one of our foci will be at the origin. So I'm going to have a foci at the origin. Okay, now I need to finish my graph. I do have a problem though. My problem is that this graph is in polar. It's not in xy coordinates. So I can't use the same properties that I had for an ellipse in the beginning, where we had, the a squared, the b squared, the c squared, and all that really nice stuff. I can't use that x squared over a squared or y squared over a squared plus so on equal to 1 because my equation is in polar form. So what I'm going to do is I'm just going to find some points. I'm going to start out with theta equal to 0. Okay? So if theta is equal to 0, remember polar coordinates, we start with theta is equal to 0 and we go counterclockwise some distance r. If theta is equal to 0, that means r is equal to 2 over 1 plus 1/2 because cosine of 0 is 1. Simplifying this and doing the algebra, I'll get 4/3. So when theta is equal to 0, then I'm at the point 4/3 out. Okay, so it's going to be between, oh, this is, I should have made this graph a little bit bigger between the 2 points. So somewhere over here is going to be a point on my ellipse. So it looks like it's going to take this shape here. And then it's going to come around. I have a foci. Remember that red dot? That's not the center. That's the foci. But we do have this property of foci, that it's going to have some distance, right? There's always that concept of distance. So we're going to have a distance between the foci and that point I just found, but we're also going to have this distance here from our directrix, and that distance is 8/3 if that's the point 4, x value of 4, and I have a 4/3 plus an 8/3 is a 12/3, should be 4. When we complete our, and I'm just going to sketch my ellipse and I'll just add in the, I'll add in the points later. This is definitely not to scale. So I'm going to have this other point here. There's this idea of symmetry. If the point to the right is 8/3 away from one directrix, then this, maybe I want to make this in red. Then this other point here that I just found has to also be 8/3. It's like putting pieces of a puzzle together. So if I figure out the math there, then my directrix is actually going to be negative 20 over 3. So I found that by doing some math in my head. But remember that this, now we're in polar, also represents theta is equal to pi. So you can always just plug in more points if you need more points. If theta is equal to pi, that means my r value is going to be 2 over 1 minus 1/2. And then doing that math, that would give me a point of 4 here. It's a distance out 4. So if I was looking at x and y coordinates, that would represent negative 4 on the x-axis. Okay, so recall that this distance here from the foci of 0, 0 to my ellipse, that distance was 4/3. So if I go a distance of 4/3 in from the point negative 4, I will have my other foci. And if we do the math there, I think I'm going to need then that point, that other foci, should be negative 8/3 comma 0, right? Because I'm subtracting. Actually not subtracting, I would be adding a positive 4/3 to a negative 4. Okay, I think I have all the information that I need. I was supposed to find the vertices, foci, directrix, or directrices of this conic section. So my foci, we already were given that one of the foci has to be at the origin. So the other one we found was negative 8/3 comma 0. So our vertices, one of those is this -4. And again, I'm not doing these in polar coordinates, I'm doing these in x and y coordinates. One of them was -4, 0, and the other one was 4/3. Comma 0. Our directrices are these two equations, these vertical lines, x is equal to 4 and x is equal to -20/3. And I think that's all the stuff we had to find. So again, it's just like a puzzle. You just have to go back and forth with the information that you know. And remember, we are in polar. So if you're unsure, just put in different theta values. And then you'll get an R value, which would be a point somewhere on your ellipse. So that's it for 12.4.